Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guest today is Hrant Gharibyan, co-founder and CEO of BlueQubit. Hrant describes the company's focus on developing quantum algorithms and software solutions for complex classical and quantum problems, such as material simulation and optimization. He describes key projects, including a DARPA collaboration involving neutral atom quantum computers and work of Honda Research Institute on quantum algorithms for image classification. He highlights the importance of hardware-agnostic approaches and the potential for achieving quantum advantage in the near future, addresses the challenges of different quantum hardware modalities, an evolving landscape of quantum computing tools and techniques, and much more. We hope you enjoyed this episode.
Hello, Hrant, and thank you for joining me today.
Hi, Yuval. Pleasure being here. Yeah, thank you for this opportunity.
So who are you and what do you do?
So I am a quantum scientist. I did a PhD in quantum physics. I've done a lot of quantum computing research for the past decade. And a year and a half ago, started a company in quantum computing space. The company is called BlueQubit. We are a quantum algorithms and software company, and I'm the co-founder and CEO of BlueQubit.
What kind of algorithms and software? Or maybe we start with who would your users be?
Yeah, great question. So I think, there are two components in developing quantum applications. One of them is much more scientific in a sense of developing novel algorithms for addressing different complex classical problems or quantum problems that are hard to solve with the current computing devices like CPUs and GPUs. For that direction, we looked into material simulation, optimization problems, for instance, are an area where classical systems are limited to solve them, and we believe that quantum computers bring a completely new toolkit to the table. And the users are enterprises who have those problems, or the governments who deal with those kind of very heavy problems at scale. And they're interested to hire researchers and scientists to focus on those algorithms. Some of those algorithms are quite well established that we adopt to the specific enterprise use cases. Some of them require a really novel insight solutions that end up being scientific papers. But then another component of quantum software is actually implementing algorithms in the quantum devices that we can access. And that part is extremely software engineering heavy. We write code in Python utilizing libraries for quantum algorithm development, and managing a product that's an enterprise grade product for running quantum workflows, implementing them, maintaining the data, and tracking the execution of various quantum algorithms on real quantum hardware and on quantum simulators.
Do you have a customer example where maybe you can talk about what their issue was or what the challenge and how you helped them address it?
Yeah, actually, I can talk about two because we are actually publicizing those. So we got a green light from the customer. One is actually a DARPA project on specific optimization problem on the graphs that utilizes neutral atom quantum computers, like the ones developed by QRA computing, which is based on neutral atom technology. They have 250 atoms, and we developed an algorithms for doing a Gibbs sampling of independent set problem. This is a very theoretical problem that we have been working on, but that once you solve it or have an idea how to solve it on a quantum computer, you can hope to extend it to actually practically interesting problems. Like in defense case, it could be sensor placement optimization, for instance, is a one use case where finding minimal number of sensors that will provide maximal coverage for some generic 2D graph that describes some neighborhood or possible locations. And that's an example. I think a lot of the work we do is very theoretical still. A lot of it is a lot of benchmarking happening on simulations as well as on quantum computers. But this is kind of to give you a flavor of one specific use case. Another use case that we work closely with a customer, and it's quite compute heavy, I'm actually gonna do a presentation about this in a couple of weeks, and we're gonna publish papers soon. We're in approval process, and it has to do with like loading images into a quantum computer with a very high accuracy and minimal number of gates. This is kind of first stepping stone to like developing quantum algorithms for image classification. And we did this examples of loading like 2 million pixel images into like 20 qubits, and then developed a novel method for breaking down image into blocks and then loading into a quantum computer. And this is a work we did with Honda Research Institutes. For example, they have a couple of team members interested in like quantum use cases, and we developed the algorithm together, then used like our GPU simulators to do the benchmarking and testing of those algorithms on a real data set, like Honda Scene data set, which is like a kind of standardized data set for image classification, like in a traditional machine learning framework. So we adopted it and carried out a bunch of experiments in a quantum simulators, as well as quantum hardwares like IBM machines and Quantinuum machines, like we did on Quantinuum's H2 chip, which is a 56 qubit quantum computer, and IBM Heron, which is a 156 quantum computer with really good like 2-qubit error rates, which is like quite remarkable. We were able to run like thousands of 2-qubit gates for like loading images and then classifying them afterwards. So this is kind of to give you like more concrete examples. But the use cases across verticals are different. Financial institutions look at a lot of optimization problems like portfolio optimization or fraud detection with quantum machine learning. And a lot of these use cases are extremely heuristic. So particularly quantum machine learning, there's no real evidence that it will work or will not work. I think there's some results on it with the very niche assumptions that things will work or will not work. But those assumptions are very often violated or not accurate enough. So it really comes down to real practical experiments and like on hardware and on simulators to like figure out what's the real potential or whatever strategy you develop.
So that's actually very interesting because data loading has been sort of considered a big problem for quantum computers. So you said 2 million pixels loaded on 20 qubits?
Mm-hmm. That's right.
And can they also be unloaded? Meaning, do you just load them or can you reconstruct the image to a reasonably high quality after that?
That's a great question. You can't with the exponentially low cost, right? Like basically you need to do tomography, but you can do operations. So if you have a data set that's already quantum, you could like do classification on them that will not require you to read out the answer, right? Like to process the images, you don't always need to kind of reconstruct it completely. You can do different operations in the like quantum space. And that's actually one of the main like messages of this work is that like loading is a one-time cost you pay, but then after that you you open a door for like different other explorations and use cases. And indeed, like sometimes there is a cost to pay to read out the data, but a lot of times you don't actually like need to read out the data fully. Like you can, in kind of a quantum compressed fashion, you can process and do operations on the data. For example, classify the data or like compute the dot product between images, like which is like a distances between different images and so on.
Is there significant classical pre-processing? Are you taking this 2 million pixel image and trying to figure out what 20 states you need to load into a quantum computer and then do state preparation? Or is the loading sort of, you have 2 million operations on the quantum computer essentially?
Oh, no, you don't have that many operations in quantum computer. It's a classical training of a quantum circuit. So you train a quantum circuit that's sufficiently shallow to be hardware friendly in the modern quantum hardwares. But then you train to find the amplitudes that mimic the classical distribution. Yeah, indeed, this is actually like the cost is polynomial in the size of the original like classical data set. And it is a classical cost, right? Like we do the training on GPUs essentially. But once you train it, you have a circuit description of your data, which is extremely efficient, right? Like it's a pretty shallow quantum circuit, like the parameters of the quantum circuit.
Would you consider your company a generalist or a specialist? Specialist meaning, we are primarily machine learning or primarily optimization or something else?
Yeah, that's a good question. I think we are a generalist. Our R&D effort has different like interest areas, including optimization, machine learning. In terms of like the very product side of things, that I kind of want to like get it out there for quantum like users who like do large scale like big experiments, like expensive simulation experiments, such as training QAOA with thousands of parameters, like beyond 30 qubits. Like we have a platform that allows you to do it with a minimal effort, and we have some kind of super users, either like academic PhD students who do a lot of numerical research, or like quantum companies who are specialists. Like we have few in like bio, like pharmaceutical direction or the other, where they realize they can leverage other companies who do like a platform and like infrastructure component. So in that sense, we are a generalist. We have this tooling for quantum workflows, specifically workflows that are like analytically hard to track, and you need numerical experiments. They're heuristic methods typically. And for those companies, we could be like simply a tool, like another quantum tool to like do GPU experiments to deploy different workflows on actual quantum hardware and compile. But in terms of like use case discovery and exploration, I think we have this kind of more research part of the team that's like mostly in the US, who actually like look into use cases that could lead to quantum advantage. Like, our team has a conviction that the hardware is really interesting because we got really good at doing quantum simulation, like tensor networks, GPUs. We know how hard it is to simulate latest 156 qubits from IBM with like that, like can do like thousands of gates, and we are at the cusp of like crossing where like it's gonna be unsimulable. Then it's gonna come down, is there anything interesting you can fit in this computer that you can do that classically will be in this non-simulable regime? I think that's going to be the first quantum advantage example. Nobody really knows what use case it's going to be. Could be some very niche machine learning task you do. Could be some molecular simulation, like prepare a ground state for some target. There was like a paper even today from Google's team, like very interesting condensed matter model, which is very hardware friendly, that like you could prepare the ground state of this that's classically not tractable with tensor networks. And yeah, like, and our like more R&D side of the team is essentially focused on that, like not really fault tolerance devices, but basically this kind of a mission of, if you have 100 qubits and you can run 10,000 plus gates on it, can you do something interesting on it that's either scientifically interesting or commercially interesting? That's classically we don't know how to solve, right? Like, and I think that's the real like path to quantum advantage in the next like 5 years. And yeah, there's a lot of quantum computers now that have this kind of capabilities, and they keep getting better and better. So I think we will see a lot of very interesting things. We saw a lot of cool stuff in error correction. I think we'll see interesting things in very niche like problems that quantum computers can solve.
What's your favorite quantum modality?
Oh, by modality, I assume you mean like hardware technology. Like, is that what?
Yes, I mean, some people like superconducting,
Yeah,
some people like others.
Make sure. Yeah. Okay, I am gonna be agnostics. I like, so I think each of the different technologies has pros and cons. Like I will list some of them. I think one thing is clear to me, like gate-based formalism is here to stay, like in terms of algorithms and hardware implementing gates. And like a lot of like everybody, even like people who started out with analog initially, they realized now like you need digital quantum computers. You need to implement gates, and we have a formalism to do gate-based algorithm development. So I think in that part, I think there's a consensus now and like growing interest, and that's why kind of we can exist now, is because there are a lot more people who like care about gates, who want to develop algorithm with gates and test them on GPUs. In terms of like performance and scalability of hardware, I love neutral atoms because they are scalable. There was a great examples on like really cool way to do error correction with neutral atoms, which is extremely promising. That this is a limitation that like is much more severe in trapped ions and superconducting chips. But the fidelities are not there yet. Like in terms of like physical fidelities of the neutral atoms are much more harder to get them down below certain thresholds. but they're easy to scale, and we have like pretty good ideas how to go to like thousands or even up to 10,000 systems. And perhaps with few layers of error correction, we can beat all the other like technologies. With trapped ions, they're extremely slow to operate and do gates on and like read out the answers. But, like we were extremely impressed with the Quantinuum's, like 2-qubit gate fidelities and the ability of doing all-to-all interactions. This is like a huge thing, is quite important. And then, and that additional slowdown, I think in a big picture is going to be irrelevant. Like it might be like 100x slower, but if you can get exponential advantage in a certain problem, we were talking about 2 to the 100 like timescale difference, 100x cost. Whether it takes a day to run or 100 days, if you're solving unsolvable problem, is like irrelevant. So I think in that sense that they I really like how the trapped ions address that, but they have a huge scalability question. I don't think people have a good idea how to scale those systems in a consistent way, like to thousands. But perhaps there would be a good way to get to 100 qubits and 10,000 gates first, and actually do the first quantum advantage experiment. Because the all-to-all connectivity allows you to do the circuits much shorter, have like more complex entanglement with very few gates. So, maybe like doing some interesting like Knez matter problem, which is like maximally entangled with some really sophisticated entanglement structure that they are able to do, and getting to 100 qubit, I think is doable. Like I think with the Quantinuum, like 56 qubit system is quite stable and like really works well. And I think they have a clear understanding how they would like scale it, right? And there are other ideas like IonQ, and there's an Israeli company we work with, Quantum Art. They have also very interesting approach on they're leveraging both like local gates and all-to-all gates, and then there's a trade-off between speed. And they have I think the in the near term, actually, trapped ions might get to a like actual advantage use case first. They're going to be much like harder to scale to production scale quantum computer. Like that you can like solve with like millions of gates. You can do Shor's algorithm or like solve like generic problems. I think they'll be much harder. Yeah, superconductors are great too, but their issue is, again, scalability is challenging, and they're 2D geometries. So basically compiling any like interesting circuit ends up resulting in a much deeper circuit that's like becomes challenging, since their fidelities are somewhat comparable to the trapped ion fidelities now, right? Like they're about the same fidelity, but all-to-all connectivity is missing there.
How do you decide on which hardware to use? So a customer comes in with a problem. Let's assume you even developed an algorithm, you ran it on a simulator. Now the customer wants to see on real hardware. Sounds like the implementation would be very much hardware dependent. So do you just do multiple implementations? What's your sort of thought process on deciding on the hardware platform?
Yeah, so I think it depends on the problem. So we are kind of like, the cool thing that the customer sometimes like, I think, like independent arbiters, because we kind of are agnostic to which hardware. So we like look at the problem and then decide what problem we want to work on. And depending on the problem, different hardware might have the right advantage, right? If it's like has an independent set-like structure, like Cura device has natural framework for it, it's larger, it has like this block repulsion internally embedded. So obviously that kind of problems are much natural to do it in that context. For the other like project, for example, the one we did with Honda, like you could go either way. And like we actually decided to do both. We did some experiments on Quantinuum, we did some IBM. We actually benchmarked like when you compile different types of circuits, whether the connectivity has a big impact on the accuracy of loading the data set, because it completely changes your ansatz architecture. So yeah, we actually did kind of independent benchmarking, and then yeah, there are trade-offs between the two. There's cost factor, there's performance factor, there's like the depth of the circuit you can run. I think it really depends what is like customer is after. If they want one implementation, really good one, then it's like we have to make sure we understand the problem well, we understand the mapping we want to proceed, and then find the best fitted hardware for that. Yeah, like for example, we're still kind of making decision. We recently got like an award on the Air Force direction for like optimization problem. There, we're actually like deciding whether in conversation with the customer to see, do they prefer more independent, but a bit shallow benchmarking of different technologies, or just make a bet on one and just really go deep in terms of the adjusting the algorithm. And it really comes down to the like customer needs, right? Like what they're more after. And sometimes there's also like a customer has a preference in advance. They already have a relationship with one of the hardware companies, and they're like, oh, we would really love to try this hardware, but we don't know what algorithm to run. And then it's a matchmaking. Do we have the right algorithm for their needs? Like can some of the existing algorithms be adjusted to their use case? And yeah, that's.
You sound optimistic about reaching quantum advantage, but I guess the question is when? What is your best estimate?
Yeah. I mean, to be clear, what I mean by advantage is like something that IBM tried to do with their utility paper, but like pushing to actually a regime where tensor network simulations, nobody will come up with a classical technique within like 6 months or a year, right? Like, I don't think it's gonna be a problem where we can like proof analytic like scaling difference. I doubt it. I think it's gonna be like heuristic thing, and it's gonna be like, oh, tensor networks give completely different answers, and maybe you can do like a physical experiment in the lab. My optimism comes primarily from the fact that if you have 100 qubits and you can do 10,000 2-qubit gates with a really good fidelity, like the regime where we're approaching now, really reproducing this like observables in the end of it classically is extremely hard. Like we did some work on like tensor network methods, which are like the state-of-the-art classical techniques. And once the entanglement is like deep enough, like, and it's built up enough entanglement, it's really no shortcuts, right? You really need to like track all 2 to the 100 possible trajectories. And that's where my optimism comes in, like that we are there. And like, in my view, like when you have that kind of capability to like simulate entanglement, there are a lot of like condensed matter problems, like very scientific problems. I don't think it's going to be like very commercially useful problem first. It's going to be some scientific problem similar to the Ising model, maybe variation of that model that's very hardware friendly, that will do like some experiment, measure some observable or like some diffusion, like speed or like whatever, like quantity. And then we can say, hey, like this is really untractable in that regime. And then we can like explore the phase numerically with a quantum hardware. And then we will not have any classical analog to predict this behaviors, which would be the first step, right, to like commercial quantum advantage. So I want to make sure that I'm clear. Like I think commercial quantum advantage will take a while, like to do like a proper commercially like useful molecular mapping. But to get to a problem where we can like show real superiority of quantum devices against classical, I think that's within like 5-year window, just from the quality of hardware and like scale and the gate fidelities we're able to do.
What do you think of today's software tools? Are they good enough to get you what you need, or do you need a software engineering breakthrough in how to write quantum software?
Oh, yeah, that's a great one. I think we have the fundamentals. Like, I think quantum is like going to be pretty similar to how AI evolved. There's a standardization of gate-based methods. Initially, there was a lot of argument against it, but people realized it's the universal framework, and most of the hardware can actually compile gate-based frameworks quite well. And I think there's a standardization on that domain. We don't need to like invent a new programming language. I don't think so. I think it's going to be quite similar to how like AI and like neurons became a standard. And based on neurons, we built like more sophisticated architectures like CNNs, tensor networks, like, transformers and so on. Like now we have the building blocks, and the building blocks are becoming more and more like standardized and accepted, and more people know how to use them. So now I think it comes down to like algorithms and testing of those algorithms, and then kind of hardware implementing those circuits efficiently. There, I think there's a lot of improvement and cool stuff going on in terms of quantum control, like doing like quantum control better, automating like error mitigation to even push it further a bit. Obviously, when error correction comes in, like you will write your code in a circuit, it will map to the error corrected version of it and execute that instead. But I think it's all going to be within like gate-based formalism, right? You'll be like expand it, and then there'll be more and more software needs for that, like to do it faster and better. But I don't think we'll like invent a new programming language. At least I don't see like from the user perspective, somebody building algorithm that it's necessary. Like, you basically have like a universal set of like building blocks with gates to like build a quantum algorithm.
What do you know today that you didn't know 6 months ago as it relates to quantum computing?
Oh, that's a great one. 6 months ago, let's see when it was. Yeah, I mean, 6 months ago, I haven't ran like as big of quantum circuits on the machines that we have access now. Like it happened much faster than we thought it's gonna happen. Like running on, like 4,000 gate circuits on 156 qubits with a very like good fidelity that there's still quite a bit of like meaningful signal. I didn't expect like that would happen like within 6 months that we'll have that system. So, like compared to a year ago, we were like running stuff on 27 qubits and like, hundreds of gates. Like things moved much faster than we thought. And I think that's like kind of encouraging and like giving me like optimism that there is a lot of like people hard working on the hardware side to make this happen. And the other one, I also didn't expect error correction to happen so quickly, like on actually 3 different platforms, like neutral atoms, Quantinuum did on trapped ions, and then recently Google results on a superconducting set, I think, like superconducting system. Like that was also like extremely fast and condensed, like basically within a little over 6 months. I think all this like 3 results essentially.
And last hypothetical is if you could have dinner with one of the quantum greats, dead or alive, who would that be?
Oh, that's okay. With the live ones, I actually had dinner with Peter Shor and John Preskill. I was like lucky enough to work through my academic career with some of the best, and like Seth Lloyd. And in terms of like dead, I think I would probably prefer Bell, like Bell from Bell Pairs. I think it was one of like a coolest ideas, like to like separate entanglement from like classical correlation. Yeah, he was a very interesting physicist. Like he came from particle physics background and kind of like invented like criteria for entanglement that really established like quantum information, right? That led to quantum computing. So I think I would probably want to grab a dinner with him if I had the chance.
Very good. Hrant, thank you so much for joining me today.
Yeah, thank you for the opportunity. This was fun.